Afternoon, everybody. Welcome to the Session 2 Repair Steel Bridges session. First paper is going to be on repairs to a truss bridge after vehicular collision damage. This is going to be co-presented by Rod Thornton of the Maryland State Highway Association and Kyle Smith of Greenman Peterson.
This is the presentation on the Maryland 355 or Monocacy River emergency repairs. This bridge is located on one of the two primary routes between the city of Frederick and Washington, D.C. On December 6, 2017, a forklift front-load garbage truck was being towed northbound on Maryland 355. As it approached this bridge on the south span, it hit the portal and also the subsequent overhead lateral cross bracings. And that was the location where it stopped. When our office got notified of the impact and the damage, well, we got some idea what the damage was. The response crew was actually out there and doing a removal of the truck, pulling it back across the span that it had just driven across. We told them obviously to stop because we didn't know the compromised condition of the bridge due to this damage. And basically we had them cut off the material that was preventing them from pulling it from the north side, and they pulled it off the bridge on the north side. This is just an overhead view. These are 153-foot spans. The overhead lateral bracings here, as you can see in yellow, and the south portal, those are the ones that were severely damaged. And of course, those are important for the stability of the overhead top cord of the truss. This is just an illustration of what members were damaged. At the time of the accident, we didn't know what loads existed in those members. And after the accident, we didn't know how much loads were still also in those members. But we did know that at that time, we didn't want to add any additional load to it. Also, where those forces went, we didn't know if where they were redistributed throughout the structure. So concern was we didn't want to add any load to it. You can see here the connections of the overhead sway bracing were still intact. And therefore, as the truck pulled those lateral sway braces, they actually pulled the vertical cords in the same direction. The truck was actually driving northbound, so therefore the east truss was the one that had the most severe damage. And you can see here at this location, just below this connection, the flange and the web were torn. And then in this location here, the top cord where it connected to the top truss was completely pulled out. There were 12 rivets there, all 12 were sheared. We did UT testing of the cord member or the gusset plate and found that the rivet holes were not damaged, so therefore we could use this in our repair. And then the lower connection to the lower truss of that same cord, the concrete barrier there prevented the gusset from being pulled over, but it resulted in the vertical cord member buckling and tearing, as you can see. So a little history about this site at this bridge. Originally, this bridge, the bridge that we have out there today, was built on top of the pier and abutments of this truss that collapsed due to an overload condition. And as you can see, it was a timber deck and very small, slender members. This is looking down that same span that collapsed. And you can note here, even after it collapsed, the stone that was in the truck actually still stayed in the truck. And the members are much smaller than the one that we have now. Also, the interesting fact is that the vehicle stayed in their correct position, unlike today with people in their cell phones. This is the picture of the bridge being replaced, and it's going to obviously much larger members and also have a concrete deck. This is the truss completed, and the interesting thing here is these two spans were actually scheduled to be installed in a site in Pennsylvania that had similar dimensions, but somehow the states negotiated and had it installed here, and therefore it took less than 4 months to actually replace the truss. So our initial response that we knew that we had to do here was we were going to close the bridge, we're going to set up a detour, we're going to get that vehicle off the bridge without causing it to collapse. We're going to come up with a means of stabilizing the bridge, and then we're going to, and also repair it. And then we needed a timeline for how long it was going to take to do all this work and get it to the public. So just like anything that we do in the maintenance area, speed is always of importance, but safety also. The general public wants this thing opened up as quickly as possible. So the fact that it was a compromised condition, it had whatever evaluation or that we performed had to be accurate because we didn't want to compromise and cause the bridge to fail. but we also wanted to open the bridge up as quickly as possible in that regard. So whatever repairs we did had to be long-lasting. We didn't want any future complications that we'd find out later on that we would have to go back and do a repair, or worse yet, close the bridge again. In a normal process of, obviously, there's plans and a lot of review. In this case, we knew we didn't have that option, so we actually did a lot of, the designers did a lot of quick sketches, sent it to the fabricator, and the fabricator started fabricating right away. This is the team that we assembled of consultants, contractors, fabricators. It just so happened that GPI was actually working on a detail of a repair at the time, so they were the lead designers. We in Maryland have open-end contracts that we allow for the construction of unspecified work, and in this case, this is emergency, so we could have the contractor out there the next day, and the fabricator that he has associated as a sub could actually do whatever we needed to do. Everything on his schedule is just changed to doing this as a top priority. First day was identify the damage. Then we had to determine the availability, what materials we need to be to able to stabilize it and do the repairs. Stabilize the bridge, actually, and then come up with a stabilization method, and then brainstorm a repair strategy, and then estimate again that time that it would take to get it done. So to identify the damage, we had two in yellow, the two overhead lateral cross braces had to be, or sway braces had to be completely replaced. One, the third one just had to have the lower cord member replaced. The portal had several components that need to be replaced also. Then from the truss side of the two vertical cords on the east and west truss had to be replaced. Near Baltimore, we have a yard that we collect all of our materials that we've used in former repairs, and also out of our capital program when we see steel that we think we could use in future projects, we have it stored there. So in this case, based on engineering judgment, we picked the quantity that had a large enough quantity and also size that we thought could be used for stabilizing, and also a frame that we were considering to actually do the repairs. All that was shipped directly to the site, and the contractor could start working. Then we also directed the fabricator to go ahead and start doing his fabrication of the components that were going to be replaced that had been identified that needed to be replaced, so he was to purchase it and start fabricating. So we kind of dualized our work there by doing that. To stabilize the bridge, this was a sketch that I sent the consultant to consider for a way of doing that. The idea would be is to sister the original cord member with a new beam that would be much larger in size. This could be installed from the south abutment without imposing any load to the bridge other than the beam itself. And once this was installed, then we could go and do our frame that we needed to do the actual repair and replacement of the damaged cords. And this is a sketch of that was sent that day, just to say, you know, we want some sort of jacking boxes, which is what these are up here in the corners. And the rest is just a frame that basically would be able to lift the cord members up and actually be able to replace the ones that were in place. So now that we've got our scope of what we plan on doing, how we're going to do our stabilizing the bridge and repairing the bridge, we sent out a notification of what we thought would be an appropriate time of 60 days. One thing we normally do in an operation like this, we do it 24 hours, but because of the severity of weather and because of the timeline for getting all this done, we figured we would schedule it saying 60 days, just working regular daylight hours. So now all that's done, I'll have Kyle give you the background on what he did for the design aspect of this.
So as he said, the first step is to stabilize the bridge. For a little background, the blue members are always in compression, whereas the red members in this illustration see tension and therefore categorized as fracture critical. Interestingly, this second vertical here was the more critical of the two because it carries a lot more load than this third one, which, while fracture critical, actually doesn't see a whole lot of demand. It's more in there for position of the stiffness of the truss. So we started with a 2D model to determine the design loads for these sister beam connections. Those two locations, we took off the worst case loading and designed all 4 sister beams for the same load. In addition, we modeled in some additional construction live load and for personnel and equipment as well as man lifts. Once we had designed the connections, this is the sketch that we provided to the contractor that they used to do the construction. It was just faster for us to put it up by hand since our engineer wasn't all that keen on CAD. And then later on down the line, we turned them into CAD drawings to give to Rod for documentation. So this is the day, the sister beam installation. It's 3 days after the impact event. You can see that only got some personnel and some scaffolding on the bridge deck. There's actually a person up here in a bucket to make the connection, but they're supported off the bridge. So after they're installed, you can see here on the left, that's the sister beam adjacent to a damaged bent vertical, and then there in the middle is next to a severed vertical. There's still a little stub of that vertical up here, you can barely see, but this is what the connection there looked like from the outside. It's connected through, we replaced the rivets with high-strength bolts and connected to that stub that's in there between the gussets. So with the sister beam connections figured out, we moved our attention to the jacking frame. And this is the sketch that we started with before we had really done all the analysis to give to the contractor and fabricator so they could start welding on stiffeners and getting things fabricated ahead of time. The truss members are outboard of the bridge deck and barrier, so that was the reason for having that cantilever section beyond the parapet there so that we could get out underneath the truss. We modeled assuming the worst case dead load any of the four members, figuring that's how high we had to lift it in order to reposition the truss and get the load back into the verticals. And you can see applying that load asymmetrically with just on one side, there's a lot of deformation there, a lot of deflection, and it was far too much to tolerate. It was too soft. We needed to have better control so we knew how much, that we were applying the load and lifting the truss rather than bending the beam. So we put in struts to stiffen it up and then moved on checking the model from that perspective. And that worked great, got rid of the vertical deflection, but still due to the asymmetry, there's some horizontal translation that was again too much to tolerate. So from there we decided to add some bracing, and that did the trick. It stiffened everything up and we felt comfortable moving forward with that schematic. This again was the preliminary sketch, and then this is what the shop drawings looked like. We used some more. Rod mentioned having some beam and H-pile sections that we used for the sister beam and the jacking frame, and then we cut some of them up, but also to use for the connections for the jacking frame and to create this bracket here. So here, 6 days after the impact, you can see the sister beams are in place. The first two jacking frame columns are up there, and they've cut out whatever portions of the overhead bracing were in the way. Here's an image of the completed jacking frame. You can see the diagonal cross bracing. We used large angle section that the fabricator had they were wise enough to order right off the bat, thinking that chances are we'll use it, and sure enough we did. We also include a cross bracing longitudinally because the upper truss cord is sloped and there was going to be a thrust, so we wanted to make sure that it was the frames were braced off one another. So again, with the sloping top cord there of the truss, we had to figure out a way to apply the jacking load evenly. So the two jacking frames were constructed to the same height, and the variation in elevation was made up by these fabricated steel bolsters that the fabricator built out of 1-inch plate that they had in supply. And that supported the jacking box, which was then underneath this jacking wedge assembly that we worked with the fabricator and figured out a good way to come up with a variable slope built-up member that it was easy enough for them to get in there and perform the welds and fabricate, and it worked out really well. So then with the sister beam connections and the jacking frames figured out, we moved our attention to modeling. So we started with this 2D model. We applied the jacking force offline from the truss panel point and determined what the moment was going to be induced into the connections due to that. And that was really our biggest concern, making sure that we didn't apply too much force to where we sort of unzipped that top cord connection and had a progressive failure as we're here trying to fix the bridge. So that was the most sensitive location due to the applied loads that we were going to be exerting on the bridge. Started off with the 2D model, and as we were doing the design development, we had another team working on a 3D model. The 2D model was great. It allowed us to quickly iterate, got conservative demands, but the 3D model we also wanted to have to compare, try and capture the asymmetry of the damage and the effects of the transverse load sharing of the floor beam and deck system. Comparison, this is what the as-built bridge looked like in the 2D model under self-weight, and then that's what the 3D model looked like. Here we've got the stress gradients turned on, so elements in blue are the higher tension, elements in orange are the higher compression. And the results, as you would expect, they matched up really well for a symmetrically loaded bridge. And that gave us confidence that, our 3D model was operating correctly and we could move forward. Then we tried to model in the asymmetry of the damage. The contractor went out and they field measured from the top cord to the bottom cord connections to determine the length of verticals that needed to order. And we compared those results to measurements from the as-built shop drawings to determine how much deflection there was in the deformed shape. And we found that by modeling 2 of the verticals completely removed and 2 of them at 50% stiffness, it matched almost exactly to the field measurements. So that gave us confidence that we had a working model. So this is a comparison of the as-built versus the damaged state. You can see there in blue and red where the bridge was taking up additional stress. The top and bottom cords were carrying a lot of load and flexure. So starting with the as-built, moving on to the damaged model, we modeled in then the sister beams and then started applying loads for the jacking operations and logging the demands on the adjacent members so that we could compare to what we were actually seeing in the field. That's where AECOM came in. Rod brought AECOM on to instrument the bridge. They put in a series of 32 strain gauges, coordinated with us to determine the locations, and this way we could evaluate what stresses were being induced on adjacent members as we're applying the jacking loads. The idea being that we have to lift up the top cord of the truss in order to reposition it, put in the verticals, and make sure that we reload the verticals. And as we do so, we want to monitor the impacts of the adjacent members, evaluate the response, compare to our predicted values, and hopefully everything matches up and we can be confident moving forward. So to go over the repair procedure, this is 13 days after the impact event. We all met at the district office about 5 minutes from the bridge. So it was Rod's people, the district staff, GPI, the instrumentation team, the inspectors, the contractor, the fabricator, and we spent about 4 hours walking through the operation, giving everybody the opportunity to ask questions, maybe raise concerns that they may have, short limitations with equipment, that sort of thing. So after 4 hours, we all caravanned over the bridge, and then we went through a test run. It's a good thing we did because we identified a few issues. One, the strain gauge data immediately showed its usefulness because one of the jacks wasn't working, even though the contractor swore it was. No readings, so they found out that one of the hoses was disconnected. So this is a look at the test run that we did. It only ran for about 35 seconds. We applied a very small amount of load. You can see there's immediate spike in strain at all the members, and then it leveled out. So that was a good test, and we compared that to our results. This is maybe a less valuable looking test. This one ran for about an hour. We did this while the contractor was demoing the parapets next to the gusset plates. We only ran it because we wanted to make sure that we'd capture if there was any major redistribution of load due to a change in stiffness, but there wasn't. This is just temperature effects. Another lesson learned from the test run is that the jacks that we had out at the site were too large. You can maybe see here the needles moved 1 tick on there, which already was double the load that we were trying to put into the test run. So from there, we decided to back down from 100-ton to 25-ton jacks, which gave us much more control. So here's some images of the contractor demoing those parapets. Here, when they're done on the left there, you can see drilled out the existing rivets and replaced them with high-strength bolts so that they could make the splice connections more rapidly. And then there on the right, the contractor had to use hand tools to get down in there and cut off the existing vertical and then grind it smooth to create a mating surface for the new vertical. It was, very, very labor-intensive, very careful work, and they did a great job. The foreman actually did it himself because he didn't trust anybody else to do it. And they did all that without damage to any of the gusset plates. So here is the first vertical that we're flying into place. We found out that there was another thing that we had overlooked. The original Carnegie sections, I think they were 10 by 49, were actually 3/16 of an inch shallower than the newer rolled shape of the same size. So when they tried to pull this into place, it took them about 4 hours to work it up there because the gusset plates were spaced for a shallower member. So afterwards, we took some time to evaluate the gusset plates, made sure we hadn't done any damage, or we didn't want to take them back out and grind the columns down. We determined that the deflection of the gusset plate was a small amount of stress that wasn't a concern. Most of the deformation was probably taken in the rivets that had probably yielded, so we drilled out the adjacent rivets and replaced them with high-strength bolts. And then this is what the splice connections look like at the bottom. The first one on the left is from the deck side. The one on the right there is from inline of the truss, and then here from the outside, where again, we replaced all the existing rivets with high-strength bolts. So then we repeated that process 3 more times until all the verticals had been replaced. That was done, that was completed by the 29th, which was 23 days after the impact. And from there, GPI and AECOM were no longer needed to oversee the operations at the site, so the contractor pushed ahead and replaced all the portal and overhead bracing based on the shop drawings. At that point, it was January 10th, and the bridge was ostensibly ready to be open. They had completed all the repairs, including patching the barriers. One final thing was a live load test to confirm that the bridge was behaving as it should have been in the as-built condition. So SHA, they loaded up 2 of their maintenance vehicles, weighed and measured them, provided the parameters to GPI, and we ran some analyses to predict the demands in the various members of the truss, and AECOM ran the live load test and re-instrumented the bridge, captured the areas around the replaced members, but also some on the opposite side of the truss to confirm that it was behaving symmetrically. After a series of 6 tests, we were quickly able to compare and find that the results matched exactly what were expected from the model predictions. We relayed that information to Rod, and he gave the go-ahead to reopen the bridge, and it was open to traffic by rush hour that same day. So I'll pass it back to Rod to give his closing thoughts.
So here you can see the actual timeline of the whole process that we went through. It was a, I'll say, Herculean effort by everybody involved. Obviously, to be able to estimate a job at 60 days and turn around and do it in 36 days means that a lot of things went right. But there were, as Kyle said, there's a couple of situations that in regards to like constructability, this whole thing hinged on that guy who was actually sometimes upside down cutting that vertical cord member between those gusset plates, because if any damage had been done to the gusset plate, there we had a location where we could have a fatigue issue. So we were concerned that whole time, but they did a great job, the contractor. And also, just as the first note says, communication. There was a seamless communication. I was talking with Kyle. He was talking with the contractor, the fabricator. It was like there's no barriers for people to speak to each other regarding a concern that they had. And sometimes this was on a Friday night, 2 days before Christmas at 8 or 9 o'clock, that we've had 2 or 3 hour long conversations, because this did occur, obviously, as all accidents do, when you don't expect them. And this was the coldest, actually, I think, on record for the state for an extended period of time. Practice makes perfect. The one thing that we definitely did, as Kyle said, we had that 4-hour session. I wanted to make sure everybody was on the same page, including the contractor, the contractor's foreman, what the process was going to be, what we were going to do when we get out there to actually load this truss. We didn't want to do anything to cause it to fail. And in that regard, we started with the least critical member when we did the repair of those vertical cords. And when all the kinks were worked out of it, then we could do the other 2 primary and the other one that wasn't as critical, knowing that we got it done the first time right. The public outreach was very important for the fact that the administration did not receive a lot of bad rap for the fact that it took us even as long as it did, knowing the fact that people's concerns of when it was going to be opened was eliminated within 2 days. They knew exactly what we expected it to take, and getting it done in 36 just meant it was all icing for them. They were happy. Let's see. The capabilities of those models actually was one of the things that I think I convinced my director that this whole process was going to work well, was the fact that when I asked for the strain gauges to be installed, and actually during the process of testing, we were actually able to prove everything was done according to the models that GPI had developed, that actually it predicted everything. So when you have that kind of assimilation of everything working, where you have the deflection measurements outside measured, you have actual strain gauge saying that it's worked and everything is working as it should, and then you have the models reflecting all that. We had the assurance that we had something that to this day we have no issues. Knock on wood, it'll stay that way. Any questions?
What software did you use to do the modeling?
The 2D model was in STAD and the 3D was Civil.
Yeah, Gosh, now I didn't look that up. I forgot. I knew the number, what it was, but yes, we do collect for the cost of it. I'm trying to remember if it was $1.5 million. It's out of my head now, the number. But yes, we did get the cost recouped.
Did you have pushback by the insurance companies or anything like that?
Well, everything that we do in regards to my office is we generate all the costs for our contractor or consultant, and then we submit that to the treasurer's office, and the treasurer's office collects. So we don't get involved with that aspect unless there's a court case, which of course every state has those in different situations, but not in this one so far. I have not heard. Fault was easily assessed against the actual, if it was the tow company or the truck waste management company that the vehicle was being towed. My guess is it was the tow company that ended up paying.
Did you have a sequence of repairs?
Well, as I said, you mean in the sense of stages, like first, yeah, well, the installation of the stabilization was first, obviously. But do you mean? Yeah, the communication was seamless. In other words, we directed as in what he would do. The consultant and I would actually concur on what he was actually to do next. The sister beams were to go in first. And then when it came to which vertical cord member would be operated on or worked on for the next, that was something that we discussed and then told the contractor what order it was to be done.
Is there anything that you learned on this project that perhaps can translate over to larger scale bridge projects that was successful that will make things go faster or go better in terms of economics, get things in terms of like whether it be the way that contracts are built, DOT oversight, something like that, because you did a lot of stuff in 36 days that other projects could take years to have done.
I guess I can only say to that would be it would be like a design build, but it would be in the case of everybody had the same goal in mind. Our contractor is a time material contract. So we have these contracts working throughout the year, and we have actually inspectors that work closely with each one of these crews. And like Kyle said, the foreman that did the work on the cutting of the cord, he took great pride in the fact that he could do it and knew that he could do it. So it was kind of like everybody was in the same direction. It wasn't like a profit-oriented type operation. Everybody was trying to achieve this project to be completed in the shortest amount of time. Where that would fit into like a future large project and how you would be able to get everybody to say, hey, I'm not just in it to make a lot of money, I'm in it to actually produce a product that is going to last and be done exceptionally well. From that regard, I mean, obviously for the contractor, and I think for our consultant firm and everybody took pride in the fact that they felt that this was going to be something that was going to be a signature repair. In other words, it got recognition in Maryland Department of Transportation. We got an award for it because it was seen as something that a catastrophe was turned around to be something that worked out very well.
Thank you, guys. Great presentation.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.